Welcome back, residents. Let's dive right into this explainer on refraction. I am so thrilled to guide you through this material today because we're going to transition from what can feel like abstract, dry optical physics straight into the high-yield principles you absolutely need for true clinical mastery, and of course, for crushing the OCAPs. Look, I know optics can feel like a daunting mountain of formulas, but our goal today is to build a deep, intuitive understanding of exactly how light behaves as it enters the human eye. We aren't just memorizing isolated facts here, we're learning the underlying physical processes that dictate how we prescribe glasses, calculate IOL powers, and interpret advanced imaging. So, let's get into it.
Here's a quick look at our roadmap for this explainer. We'll start with Fermat's principle of efficiency, then move into quantifying refraction with Snell's law. After that, we'll cover total internal reflection, the paraxial assumption, and wrap up with calculating spherical refractive power.
All right, part 1, Fermat's principle of efficiency.
To really understand refraction, we first have to understand the inherent motivation of light. So I want to pause here and ask you a classic board-style question to get you thinking. Imagine you have point A out in the air and point B suspended deep within a solid block of glass. What is the absolute most efficient path for a light ray to get from A to B? Does it just shoot in a straight line to minimize the total distance, or does it try to minimize the time spent in the glass, which slows it down? Take a second, lock in your answer.
Okay, so if you guessed a straight line, you're relying on basic geometry. But optical physics, it works a bit differently. You see, a straight line would mean a lot of time spent in the glass, and glass is what we can think of as optically viscous compared to air. It has a higher refractive index, meaning it slows the light down significantly, kind of like trying to run through water instead of air. Alternatively, minimizing the time in the glass by taking a sharp angled path would result in a massive overall distance. So, what does light actually do? It follows Fermat's principle of least time. Light inherently optimizes its path efficiency. It finds the absolute perfect compromise between the total physical distance traveled and the optical viscosity of the media. It's truly a beautiful phenomenon. Back in the 17th century, Pierre de Fermat predicted this optimization tendency. Basically, light will bend just enough to make its overall travel time as short as humanly possible.
Now, Fermat's principle perfectly encapsulates the challenge facing every lens maker. To fashion a perfect lens, you need every possible pathway from the object to the image to have the exact same travel time. When you achieve that, boom, you achieve perfect focus. But here is a major Borb pearl. Fermat's principle is entirely qualitative. It tells us the general tendency of light. But to actually manufacture a lens, whether we're talking about a pair of spectacles or an intraocular lens implant, we need a quantitative formula. We need exact math. And that brings us to Villebroord-Snell.
Which brings us to Section 2, Quantifying Refraction with Snell's Law.
Let's transition into the mathematical breakdown of refraction. Don't let the math scare you. This is the law of refraction, Snell's law. Ni times the sine of theta I equals Nt times the sine of theta t. While it might seem a bit, inelegant compared to Fermat's simple idea of efficiency, this equation is incredibly powerful. It allows us to mathematically predict exactly how much light will bend when it crosses any flat optical interface.
Let's break down every single variable here step by step, because misidentifying these is a classic board trap. First up, we have the normal. The normal is an imaginary reference line drawn perfectly perpendicular to the surface of the interface. This is absolutely critical, guys. All of our angles are measured relative to the normal, not relative to the surface of the cornea or the material itself. Do not confuse this on test day. Next, Ni is the refractive index of the material the light is leaving, and Nt is the refractive index of the material it is transmitting into. Finally, we have theta I, which is the angle of incidence, and theta t, the angle of transmission. Both of these angles, again, are measured relative to that perpendicular normal line. This one equation dictates exactly how light behaves at any flat interface.
Okay, moving on to Section 3, Total Internal Reflection. Let's shift our focus to a specific, highly testable scenario, predicted by Snell's law. Time for some active retrieval. Imagine you're shining a light from inside a dense material, let's say the aqueous humor, outwards into a lower index material like air. As you tilt that light source, making the angle of incidence wider and wider relative to the normal, what happens to the light ray? Think about what Snell's law predicts. As that angle continues to grow,
Well, as that incident angle gets steeper, the angle of transmission gets closer and closer to 90 degrees. And eventually you hit this magic threshold called the critical angle. At this highly specific angle of incidence, the light doesn't pass through the interface into the air anymore. Instead, it's refracted exactly 90 degrees to the normal. It effectively skids right along the boundary between the two materials. This is the exact physical threshold where forward transmission entirely stops.
Now, if your angle of incidence is even slightly greater than that critical angle, you get total internal reflection. Absolutely no light is refracted across the interface. The light behaves as if the boundary is a perfect mirror, reflecting entirely back into the higher dense substance. And here is a massive OCAP pearl for you. Total internal reflection is the exact anatomical reason why you cannot just look at the trabecular meshwork at the slit lamp. As light leaves the anterior chamber angle and hits the tear film and air interface, it exceeds the critical angle and just reflects right back into the eye. That's why we have to use a gonioscopy lens. We literally use it to break that total internal reflection. Always remember that clinical application. We also see this used practically in fiber optic communications to transmit massive amounts of data.
All right, Section 4, the paraaxial assumption.
Up to this point, we've only been talking about perfectly flat surfaces, but the human eye, and specifically the cornea, is decidedly not flat. So consider this rather significant problem. We established that Snell's law relies entirely on measuring against the normal, but on a curved surface, where in the world is the normal? The reality is, the normal is constantly changing at every single microscopic point along that curve. If we had to calculate Snell's law for every single independent ray of light hitting a curved cornea, well, the math would be virtually impossible.
So to survive the math, we have to make an assumption. And this is a massive, fundamental concept for your board exams. We rely on the paraaxial assumption. When dealing with refraction at a curved surface, we agree to work only with paraaxial rays. Making this assumption allows us to treat the relevant light rays as an aggregate, a single manageable bundle, rather than performing an infinite number of highly complex individual calculations. It saves us.
So, what exactly defines a paraaxial ray? The test makers absolutely love to trick you here. To be considered paraaxial, a ray must meet two strict criteria simultaneously. It must be close to the optical axis, and it must be nearly parallel to it. Watch out for these classic board traps. Trap number 1, a ray that is close to the axis but intersecting it at a sharp angle, that is not paraaxial. Trap number 2, a ray that is perfectly parallel to the axis but located way out in the periphery of the lens, also not paraaxial. It must be both close and nearly parallel. Lock that in your memory.
Finally, Section 5, Calculating Spherical Refractive Power.
Let's tie the paraaxial assumption and Snell's law together into our most high-yield mathematical formula. When we agreed to only look at paraaxial rays, a mathematical miracle happens. The complex sine functions of Snell's law condense down into this beautifully simple, elegant equation. Power, measured in diopters, equals n prime minus n, all divided by r. This is your reduced power formula for a curved surface. Let's step through exactly how you execute this formula in a clinical or exam setting. Step 1. Identify n prime. This is the refractive index of the material where the rays are going. Step 2. Identify n. This is the refractive index of the material where the rays are coming from. Step 3. Find the difference between those two indices. And Step 4. Divide that difference by r, which is the radius of curvature of the refracting interface. It is a straightforward, simple calculation, provided you just keep your variables straight.
Let's wrap this explainer up with our top OCAP pearls for this formula. First, just look at the direct mathematical relationships. Refractive power increases as the difference between the two refractive indices increases. Second, because r is in the denominator, power increases as the radius decreases, meaning a steeper curve gives you more dioptric power. But here is the most critical, often ignored assumption of this entire equation. The refracting interface must be completely spherical in shape. Why? Because only a perfect sphere has a single, constant radius of curvature to plug in for r. So I want to leave you with a provocative clinical thought to ponder. If this formula absolutely demands a perfectly spherical surface, what happens when you are looking at the corneal topography of a patient with keratoconus or high astigmatism? How does this beautifully simple equation fall completely apart when we introduce multiple radiuses of curvature? I challenge you to keep that clinical reality in the back of your mind as you move into your astigmatism modules. Thank you so much for joining me for this explainer. Keep reviewing these foundational concepts, connect them to your patients in clinic, and you will absolutely build the clinical mastery you need. See you next time.